Hello everyone. Welcome to my presentation, Modeling of Stainless Steel AISI 316L in Finite Element Simulations. This presentation originates from a master thesis written by Kristian and Lars, who are former students at NTNU in Norway. And the thesis was supervised by myself, working in Multiconsult, and Arild, who is a professor at the Department of Structural Engineering. First, a few notes on the motivation for the study. Of course, structures placed in harsh environments are susceptible to corrosion, and sometimes reduction of maintenance cost might call for stainless steels. And depending on the application, these structures can be subjected to large plastic deformations, rapid loadings, various temperatures, which need to be accounted for in the design process. An example could be a ship collision in the Arctic environment, for example. Now, the main tool for designing structures like this is the finite element method, widely used. And to achieve accurate predictions of stainless steels, it is required that the material is well described in the numerical model. The study consists of 3 parts. In the first part, we carried out uniaxial tension tests at 5 different temperatures ranging from -20 to 200 degrees Celsius. And we studied 2 different strain rates, 10 to the -3rd and 10 to the -1st per second. And we did 2 replicate tests at all conditions. In the second part, we calibrated 2 different material models, one phenomenological Johnson-Cook model and one model consisting of piecewise stress-strain curves. In the third part, we validated the material models with the plane strain tension tests, and we carried out numerical simulations of these tests. All the specimens were milled from a 5 mm hot roll plate. We used the traditional dog bone specimen with a rectangular gouge area, and we used a regular tensile testing machine to pull the specimens all the way to fracture. They were placed inside a heating chamber, and we used a digital camera to monitor the surface during the test. In addition, we mounted some thermoelement threads so we could have some sort of temperature measurement during testing. Here we see an overview of the uniaxial tension tests where we see the effect of temperature. On the left side, we see the low strain rate, and on the right side, we have the high strain rate tests. During testing, we took pictures with digital cameras, and then we performed digital image correlation to calculate the true stress and strain all the way to rupture. This was unfortunately not possible for the low temperature tests, -20 degrees, but we have presented the data as far as we could. What we can see is that we have significant softening with higher temperature and also a reduction of the rupture strain. This is true for both strain rates we have investigated. Here are the same curves plotted to see the effect of strain rate. So for each of the 5 different temperatures, we plotted both strain rates together. The black curves are the low strain rate and the red curves are the high strain rate. And we see a clear effect of the strain rate, especially for the low temperatures, for strains above 50% approximately. We see a lower rupture strain and also lower strength. And the lower strength is a little bit surprising, but we think that this is due to adiabatic heating of the specimen due to plastic deformations. So if you recall the previous slide, we saw a quite significant softening with increasing temperature, and we think that that is the reason. If you recall previously, I mentioned that we had thermo element threads mounted on the specimens to measure the temperature. So we didn't know exactly where the necks would occur, but we had some tests where the neck occurred quite close to the thread, and we measured temperature increase of approximately 100 degrees. So that is quite significant. So that's why we believe that the softening we see here is due to adiabatic heating. For the high temperatures, the effect of strain rate is smaller, and it's most visible in the rupture strain. So let's jump to the next part where we try to simulate the uniaxial tension tests using 2 different material models. The main difference between the models is how the hardening is represented. And for the first one, it is a Johnson-Cook type model, where the equivalent flow stress is a function of the equivalent plastic strain, the plastic strain rate, and the temperature. So we see it here. We have a factor with the yield stress plus a hardening function. The hardening function we used, we see it here, was a 3-term Vauci model with a bunch of material parameters that were fitted to the lowest strain rate 20-degree test. And this factor is multiplied with a factor containing a dimensional plastic strain rate, which is seen here, where we have the plastic strain rate and reference plastic strain rate. So this is chosen. And then we have a factor containing the dimensionless temperature. We see it here. So there we have 2 parameters, the reference temperature chosen, and then we have the melting temperature. So all the parameters in red are calibrated to the experiments. The second material model is a piecewise model suggested by DNV-GL. It consists basically of 3 parts, actually 4, but since we have no yield plateau, we skipped that part. So the first part is a linear part, and then we have a second linear part, and then this is followed by a third part, which is described by this mathematical expression we see here. It contains several parameters that need to be calibrated. This model has no strain rate or temperature dependency incorporated, such that it has to be fitted at each strain rate and temperature of interest. So for each of the set of tests we performed, we calibrated this model. Some other features of the material models. In both models, we used isotropic and linear elasticity. We used the von Mises yield criterion, which means it's isotropic. And we used associated flow rule, which means that the plastic increments are determined from the Mises function. In addition, in the Johnson-Cook model, we incorporated a failure criterion. We used the extended Cockcroft-Latham criterion, which is quite simple. It contains only one material parameter, WC, and we determined that by inverse modeling one of the uniaxial tension tests. Then the damage variable is calculated during the simulation, and the element erodes when the damage parameter reaches 1. So let's look at some results. Here we have experimental and numerical curves for the low strain rate and 0 degrees Celsius for both models. So Johnson-Cook on the left side and DNV-GL on the right side. And as we can see, both models capture the initial part of the test very well. It follows quite accurately the curves all the way until softening and rupture starts, where we see that softening and rupture occurs earlier in the simulations than in the tests. The force displacement history is also well captured at 20 degrees, and the predicted failure is very close to the experimental observation. But this is somewhat expected, as the hardening curve for the Johnson-Cook model and the failure criterion were fitted at these conditions. I also want to highlight the results of the simulations at the high strain rate and 200 degrees. We see on the left side that the Johnson-Cook model simulates failure way too late compared with experiments. But the first part of the curves are quite well matched. The DNV-GL model in this case provides a more accurate description. So let's have a look at the last part, validation of the material models. To do this, we carried out plane strain tension tests. We see the test setup on the left, where we have a very similar setup as the uniaxial tension tests. And on the right, we see the finite element discretization of the test specimen. So we adjusted the deformation rate in the tests to correspond to the same strain rate as the low strain rate in the uniaxial tension tests. Here are the results of the simulations at 20 degrees. We see that both models, they overshoot the force, but the displacement at failure is quite well captured. Remember that only the Johnson-Cook model had a failure criterion incorporated. At 200 degrees, we see that the Johnson-Cook model overshoots the force again, and the displacement at failure is way too high compared with the experiments. The DNV-GL model provides again a more accurate solutions at 200 degrees. For this model, there was no failure criterion incorporated, but the curves were clipped at the same force level as the corresponding experimental tests. So we see that the DNV-GL model seems to perform better than the Johnson-Cook in this situation. So let's conclude. The material at hand is very ductile. I've seen true failure strains up to 1.5, which is very high. And we have seen that it is very sensitive to temperatures, but not very sensitive to strain rate. At least for the ranges we have studied here. The two material models were calibrated from uniaxial tension tests. One Johnson-Cook type model, where we have one set of parameters covering all the conditions, and one piecewise DNV-GL model, where we have separate set of curves for each rate and temperature. So in general, the DNV-GL performs better than the Johnson-Cook model for conditions far from the baseline test, which were used for calibration of the Johnson-Cook. If we're closer to the baseline test, they perform equally well. And for the Johnson-Cook model, we incorporated a failure criterion as well. So with that, I would like to say thank you for listening, and any questions are welcome.